name is Amanda, and I'm a UX developer at DockYard, which is a cross-platform user experience design and development consultancy based out of Boston, Massachusetts. There. Today, we're going to talk about creating better user experiences for data visualizations, specifically when creating them for the web and things we should be aware of. It's our responsibility as designers and developers to make sure that they are accurate, effective, and accessible. So we can look at data visualization from two perspectives, the encoding side and the decoding side. The encoding side is when we are designing and implementing the graphs, and the decoding side is the use of the graph. So after this introduction, we'll decode several data visualization implementations to help inform our decisions for encoding in the future. Data visualization encoding is really big in scope and includes a lot of research and analysis, as well as iterating over certain steps. But today, we'll focus on the last few, which includes represent, refine, and interact. We'll look at this from the roles of design and development. We can call the design side visual encoding and the development side web implementation. So what does it mean to be responsible? Oops. How can we represent our data honestly? How can we be more inclusive? And how can we make the experience of viewing and understanding our graphs better for the audience? I broke this down into 6 different sections. Oopsie. Form, integrity, efficiency, performance, accessibility, and maintainability. The first 3 are more design-related, and the last 3 are more development-related. First, we'll focus on form. Visualizations are here to help organize the information presented in such a way that users can analyze the data better, easier, and faster, so they can see and retain more. So we'll begin with choosing the right graph. This is hard because there are so many types of graphs out there. How do we figure out what will work best for us? If we don't know where to begin, we can take a look at this chart that can help us choose a basic visual representation according to purpose. We should begin with what message we'd like to convey. The purpose for many graphs falls under one or a combination of these 4 categories: comparison, distribution, composition, and relationship. It's a hard thing to choose, but we have to be careful because some chart types aren't meant for conveying certain messages. This is a zoomed out version of the previous slide, and it shows a few graph types that can fall under those 4 categories. If we wanted to show the demographic percentage breakdown of a classroom over the years, it would follow down the path of composition, changing over time, and we could choose the 100% stacked area chart. We wouldn't make a bar chart, even though bar charts are a very effective way of charting. Using a chart for an unintended purpose is becoming very common because it's getting easier and easier to create graphs now. Sometimes it just takes one click for the person who's creating it to switch it from one graph type to another. There are numerous tools out there for making charts, and here are a few. But the easy access to tools is not the problem. We as creators need to know what we're doing so that we can make informed decisions when choosing our graph type. In order to retain integrity in our charts, we should display our information correctly and not skew things in a way that slips things past our audience. Sometimes this happens unintentionally, so we should be aware of what to look out for. For example, here we have a pie chart, and pie graphs show shares of a total, which is 100%. But in this chart, we have 70% plus 63% plus 60%, and that totals to 193%. But that doesn't mean that the information is incorrect. People polled may have been able to back more than one candidate, but it's definitely confusing and allows for incorrect assumptions. We also have the red section in back, which should be the largest according to the numbers, but it's projected on a tilt, so being farther back, it appears the smallest. So we just saw a couple things that can mislead a viewer. What are other things that can have that same misleading effect? When we are creating bubble charts, we should accurately size our bubbles. And here is what I mean. Here we have a bubble chart that shows the relationship between years competed on the x-axis and the number of championships on the y-axis. The third dimension tells us how valuable that franchise is by having bigger bubbles represent more valuable franchises. So here, teal stands for American football, and orange stands for soccer, etc. If we take a closer look at the legend, we see that the middle bubble stands for 1.5 billion, and the bigger bubble stands for 3 billion. So technically, the middle bubble should be half of the big bubble. But when we superimpose that middle bubble onto the big bubble, more than 2 of the middle bubbles fit inside. So what happened here? Diameter was doubled rather than area. So how does that change our overall perception of the graph? Going back to this, we tend to see area rather than height, the way these data points are represented as circles, rather than bars. Doubling the height more than doubles the area, so this exaggerates the extremes. If we consider the middle circle to be the correct size, then the big circles are perceived as disproportionately bigger and the small circles smaller. Whereas here, we have area linearly scaled, so there's no exaggeration. The smaller circle is proportionally 1/5 of the area of the larger circle in the legend. Truncated axes can also trick people if they don't examine the graph closely enough. Here, we see the relationship between production budget and box office sales for a bunch of different movies. Zookeeper, which is in pink at the very bottom. At first glance, we see Zookeeper, and it sits on the bottom line, and so we could assume that maybe it made nothing in sales, but that doesn't really make sense. And here, it is a little less confusing. Even though Zookeeper is the lowest in sales relative to the data set, it isn't at 0. We avoided the confusion by setting the origin to 0, 0. This particular tool, which is called raw by density design, does not set the default to have 0, 0 be the origin. So it's easy to truncate the axes by leaving it unchecked. However, this isn't a rule that can't be broken. One are times that we want to truncate the axis. It's popular in stock prices, so stock prices are an exception where it's kind of necessary. This is a chart for Google stock where we have relatively small fluctuations in the data that are meaningful. So truncating the range to show these variances is practical. Having a baseline at 0, in this case, wouldn't utilize space very well. So we need to think about the design decisions that we make. Could someone looking at the graph for the first time be misinformed by how we are representing things? The moral here is to not be tricky, or at least not to be tricky by accident. Now we have efficiency. Efficiency refers to the speed at which viewers can comprehend our graphs. What can we do to help our viewers comprehend our graphs faster? Having something represented like this probably doesn't help us understand the content faster than if it was in another layout. Maybe a standard table could have worked better in this case. So if this doesn't help, what are things that can help us understand a graph faster? This section looks at different ways charts can incorporate legend alternatives to make it easier to figure out what a graph is trying to show. Sometimes legends are necessary, but they require the user to look at separate information away from the core part of the visualization. Because of this, they don't always make for more efficient experiences. If we take a look at this chart that compares the Clintons in a poll by New Hampshire voters, we can see that the legend is below only the first chart. We have to look below the chart, specifically below the first one, to see where it's written out, to understand what red, blue, and gray mean. So maybe a swatch would be better in this case. It creates an additional thought process the user has to go through to interpret the graph. Instead, this chart uses inline labels, a popular alternative to legends. This web implementation of inline labels for a line graph has some labels permanently revealed and uses hover interactions, like so, to display additional player names and their number of touchdown passes if they aren't already shown. This is a similar solution, but everything is shown upon hover, including the X and Y value of the year and salary. This method makes for a clean, non-crowded interface, but no written information can be seen without interaction. And here is a solution for an 100% stacked area chart. It shows where people living in California were born, broken down into percentages. This was made with SVG, and they used TextPath to have the label follow the shape of its section. The legend below is used to decode the colors, but it's not exactly necessary because all the information is already in the labels. In all of these cases, we didn't need to reference a legend, which allows us to focus on the visualization. Users should be doing as little work as possible to understand the content. We want to avoid creating extra work when there can be alternatives. So, this begins the portion of the talk that has to do more with how things are developed. One side of performance is the time it takes for the chart to load. Things like following best practices for loading CSS and JavaScript and loading content asynchronously help with optimizing the critical rendering path. Aside from performance, that has to do with load time, there are also things like certain CSS declarations that can be slower, so we need to be aware of which are less performant than others and weigh the cost of using them. This also applies to CSS declarations for user interactions like click, hover, and scroll. Certain styles that change upon user interaction affect layout or paint and can cause jitteriness. Besides transform and opacity, many other transitions are less advised to use. So not all of this falls on developers. Things have to be designed in a way that allows for performance CSS as well. Getting back to this diagram, let's make sure we design, implement, and test for performance and optimize where we can. Because performance is user experience as well. In this section, I'm defining accessibility really broadly. I see it as helping anyone and everyone access the visualization, which includes things like sharing it with a URL, sending it out in a tweet, viewing it across different devices, as well as the standard definition of being designed to enable people with disabilities to perceive, understand, navigate, and interact with the visualization. First, we'll start with the standard definition. There are 4 general categories of disabilities that affect web usage, and those are visual, motor, auditory, and cognitive. We'll go over several case studies and look at things that were done well or could have been improved under visual and motor. For visual, a more extreme case is blindness, but there are less extreme conditions that affect web usage, such as low vision and color blindness. So let's take a look at this chart by Podio that visualizes the daily routines of famous creative people. The legend up top shows that different color swatches stand for certain activity types. So we have teal standing for sleep, and we have salmon standing for creative work. We'll look at this in the context of low vision and colorblindness to see if it passes some accessibility tests. So this snippet came from the head of the document and allows for responsive design. It's good that maximum scale wasn't set to 1 because setting it would disable the pinch zoom functionality on mobile devices, and users should be able to zoom in on small type if they want to magnify it. So it's good that zoom is allowed. Color blindness affects people's ability to distinguish certain colors, and this Chrome extension that I'm going to demo in a second, which is called Spectrum, helps us test different types of color vision deficiencies. So here is the test for protanopia. We can see that it does pretty well. We can still distinguish all the colors from each other. But here we have more of an issue. So right around here, the change is very subtle. So that would be the difference between creative work and admin work. And with tritanopia, it seems to work fine. So there could be improvements, but most of them do pretty well. And that's important because this relies on colors a lot to see how, if there are any strange sleeping patterns or irregular work hours that this specific person was doing, so we can compare it to others or compare it to your own schedule. Here is a pie chart from Google Analytics acquisition section that shows the channels where users are coming from search engines, direct traffic, and referring sites. And it also relies on colors to decode it. So let's see how well it works with deuteranopia, which is one of the most common types of color blindness, and the main color problems are red and green. Oh, wait. Okay. So we can see that it doesn't do very well, but thankfully, the legend has all the information that is necessary. But this kind of renders the visualization useless. So the previous was a screenshot from 2012, and it's been updated, so now it looks like this, but the colors weren't changed. Now there's a hover state directly on the chart to label the sections. And the sections are ordered from noon clockwise in order of magnitude, which is an improvement from this, which is like, I think it's from 3 o'clock, but not really sure. So if these colors still don't work well, what are some that do? Here in the first column, there's a set of colors that are unambiguous to people that are colorblind and non-colorblind. The second, third, and fourth columns are color vision deficient simulations of that first column. Even with this, we probably want to think about how we can avoid using color as the only differentiator between things if they are critical. To help users that need assistive technology like screen readers to access our charts, we need to start with Semantic HTML, which means using tags in the right way so things can behave as expected. So what does Semantic HTML look like? It could come in the form of a table like we have on the bottom left. Even though it didn't have to be this way, the SVG chart above wasn't built accessibly, so it's good that there's a table underneath with all of its elements and cell elements broken down properly, with a T head, T body, and a T footer holding THs and TDs. It could also come in the form of a description list with definition terms and descriptions, or a list with list items. In addition to markup, In addition to markup, our CSS can also trip up assistive technology, so we should be testing it with screen readers to make sure everything is working as expected. Now let's go back to our list example and take a better look at it. Here we have GitHub's page for Ember.js's website, where we see what coding language takes up what percentage of the repository. So let's go over a couple things before we jump into VoiceOver, which is Mac's built-in screen reader. So we have 4 languages in order of magnitude. We have HTML, CSS, Ruby, and JavaScript, going from most, which is HTML at 35.7%, and least at 14.4% with JavaScript. And the legend relies on color, but all the information is already written out. So let's see if this is screen reader accessible. Okay.
VoiceOver on Chrome, Ember/website window, scroll area has keyboard focus.
It should be reading stuff. But we can check what it's supposed to say.
Switch link,
okay,
link, visited link, HTML3 5.8%. Visited link, CSS 3 1.4%. Link, Ruby 1 8.5%. Link, JavaScript 1 4.3%. VoiceOver off.
So we can hear that it was built properly and the screen reader is working as it should be. So we can usually tell when we inspect it and see clean semantic HTML. So as you can see, it's simple. It's an ordered list with list items, an anchor tag, and spans that have all the content shown right there in the DOM. Examples of motor disabilities that affect web usage are things like slow response time and limited defined motor control. We want as many populations as possible to be able to use our visualizations. And because blind users and users with low mobility have trouble using a mouse to interact with web pages, sites with no keyboard support are considered inaccessible. Going back to the same language percentage example, each language is a link to a list of files written in that language. And to signify focus, they kept default browser focus styles, which is easy to recognize. So we know exactly where we are on the page, and if we tab, it would go to Ruby. And we know that clicking would take us somewhere or show something. It's necessary to know where we are on a page because we are navigating with a keyboard. This is similar to using controllers on a Game Boy interface. Here, the arrow indicates where we would go if we clicked on that link. And here, there is a white border around our focused video when we use Netflix on a smart TV. So that's when we're using a remote control, maybe. So we just need to think about that when we are building our websites. And some people use a keyboard to navigate through our website. So these are visual indications. These visual indications are important because they are an affordance. They signify interaction. We can click on it to go somewhere or show something, so to take away that signifier would hurt usability. And here is a graph, or 2 graphs, that shows the number of commits in a year view and a week view. It tells us in the top right-hand corner that we can use the left and right arrow keys to change the active week back and forth. So that's what it looks like. These weren't built as links, so we can't tab through them like we would with links. So it's good that the arrow solution is here. GitHub has a lot of keyboard functions across their application and not just their graphs. Accessibility features like these don't only help people with certain disabilities. It makes it more usable for people with limited muscular control. But it's even better that it's more efficient for everyone. Being able to share URLs of what we see helps other people access our content. For example, next up we have an application for Google Books called the Ngram Viewer. And it shows the frequencies of words found in sources printed between 1800 and 2008. So when we have an interactive chart like this, we can fill in different words into the input or select something from the dropdown and see different graphs. We want to be able to send the URL to someone else and expect them to see the same thing rather than having to plug in exactly what we typed in and having to give them all those instructions. So we're usually in luck when we see the social media widgets that we see on the top right-hand corner. It's also good for keeping browser history. And the next section is about being able to access a visualization from whatever device we feel like using. So let's look at the daily routines of famous creative people again in the context of responsiveness. So let's play around with it first and see what are things that could be improved or parts that are good. And we'll take a look now. When we scroll down, it becomes fixed and the timeline is there, so we still know at what point in the day these activities are happening. And we have a filter up top. So if we click that, then it only shows the exercise. And if we unclick everything, then all of it comes back. So it will never look broken. So those are all good things. And we can hover to reveal details about that activity. So if we have a hover, what happens when it is in a mobile view? So here, all right. So what happens, what they created as a solution is that we can click certain sections and the description is now on the bottom. So are there issues with this? There are some parts that the sections are really close to each other. So is it possible that we could fat finger it? A recommended target size is 44 pixels by 44 pixels. So this doesn't really pass that test. So is there another way that we know on a phone when we click that first yellow section if we click that one or this one? You know, we can have some type of change happening to make the user know what exactly they clicked on, even if it takes multiple tries. And what also happened is here we have the break between, it changes from mobile at 800 pixels. So anything below is treated as touch, and anything above 800 pixels, they do hover. So those things aren't always exclusive. So we can have a mobile phone that uses a stylus, or we can have a desktop screen that is also a touch screen. So maybe instead of breaking it at the media query points of 800 pixels, we could do something like touch and no touch. Thank you. So this definition of accessibility is really wide, but we should do our best to think about as many populations as possible. This is a really important section because accessibility has so much to do with UX, since solving accessibility issues for people with disabilities creates better user experiences for everyone. Maintainability refers to how flexible the code is and how easy it is to modify it. Is it intuitive to update? Or do we need to make the same changes in multiple places to get things to look right? We'll look at a few graphs and see how they are from a maintenance point of view. So a few things we can look at are how flexible it is in width and height. Is it okay if we need to fit it into a different screen width? So if we started a project and it was supposed to be desktop only, and they come back to you with an increase in scope, do we need to redo a bunch of code, or is it mostly flexible and we only need to change a few things to make it work on mobile as well? what if the information isn't static? Does the design allow for varying lengths of copy or for the data to be dynamic? And can we be more terse with our code? Are we repeating ourselves? And hopefully there's comments where it's confusing. So here we have the stats page for rubygems.org. And it ranks the top 10 most downloaded gems, and there's a different color for each gem in the list. So how is this from a maintenance point of view? How future-proof is it? So what I did was I made a JS bin of this chart in like a pared down version. So it's just a little less complicated, but most of the styling is still there. So if this chart changes from the top 10 to top 25, is everything still okay? Let's check that now. So everything's cool still. It's not ordered properly, but that's because of the code I put in. And no matter how many more gems we add, the list will just get longer, and we can just scroll to see more of them. But this wouldn't be the case if it was a vertical bar chart. If we had them all as columns, then if we added more categories, they would get really skinny and squished. And so that would be a little less flexible in this case. And what happens if a different gem breaks into the ranks and has a really long name? So does the chart break then? So I found, the longest one I found was this one. Called C3 Active Record Oracle Enhanced Adapter. And gems don't have spaces in them, so it doesn't naturally break like other words would. And it pushes it a little to the side because there's a little bit of a margin on it, on the gem name. So what can we do to fix that? Okay. There are a few solutions, but here's one of them. And we could do Wordbreak break word so that it cuts it off. So now enhanced is split, and the first part of the word is a line above the rest of it, which might not be beautiful, but it's a better solution than having the graph indented. And there's a little bit of extra white space below that, below here, but to me this is reasonable. And we also have the width being pretty flexible, even though here we have a bit bigger exaggeration of things that are very similar. So that shows the difference a little better than if they were closer. But all of these are relatively good. Here's a donut chart, or if we want to be healthier, we can call it a bagel chart. And it is very similar to a stacked bar chart, like the GitHub coding language breakdown example from earlier. So we'll take a look at how future-proof this is in design and implementation, which is based off of Leah Vero's SVG solution for creating pie charts, which is in her book CSS Secrets, and there's also a Smashing Magazine post on it. So here we see like this, it gets really big. So it takes up a bunch of, we could set a max width and all this stuff, and if the screen width is more narrow, it takes up a lot more vertical space compared to a horizontal stacked bar chart. So we might think about what form of this graph would be best for our situation, especially if we need to work across different devices. So that's like medium okay. And we can look at how easy it is to add another section. So what we do is we add another circle element into that SVG. And it was pretty easy, but we had to add a stroke dash offset of -12, or else it covers our first section. So what we need to do is push that over to whatever this one is valued at. So that's medium okay. But it is set up to allow for dynamic data by changing the first number in stroke dash array. So this is good. So we can use scripting to change that number, and everything would work fine without any adjustments. And we can also change it to a pie chart really easily. So this is basically Leah's solution. We have right now a stroke width of 2, and we can make it bigger. So now it's a stroke width of 12. But if we have it so it closes that gap, then we have a pie chart. So to be able to switch it from a bagel chart to a pie chart so easily is good. This last example is a scatter plot. And I also created a pared down version of this to see how future-proof it is. Oh, shoot. I didn't mean that. So we can shrink and stretch the width and height of this graph, and it is super flexible. It could fit on a watch interface, no problem. We would see everything. It is very flexible in width and height. And it's definitely responsive. It also allows for many points of data when there's, okay, so if there's a bunch of points, and there's so much that points start overlapping with each other and creating blobs, we can switch the opacity to something less than 1, and then we can tell by density how much concentration is in that area. We can also, let's see. It also allows for an additional dimension, so not just X and Y, by increasing the size of the data points and effectively turning it into a bubble chart. So here's the demo for that. So scalable, yeah. So, yep, keep your code dry. So as a review, we should start with what we are trying to show, what message we are trying to convey, and then get into what chart type would be effective in conveying that message. When we are refining our representation and thinking about interactions, we should make sure that our code is performant, accessible, and maintainable. Here is a list of a few resources I found helpful for this talk. And that's it. Thank you.